have the next speaker, Vladimir Braverman from Johns Hopkins. Tell us about universal sketches.
First of all, thank you. Can you hear me?
Yeah.
Thank you for organizing this workshop and this program and for inviting me. I'll talk about universal sketches, and it's a collaboration with many people, as you can see. My students, my former students, Robbie, who is here, David, who is here as well, and many others. And some of the students, for example, Lin and Zhao Xing, are on the market or will be on the market soon, so please consider hiring them. All right, let me start with a question. So this is what I will do. I will talk, give some introduction, then we'll talk about some motivation in the area of software-defined networks, and then I'll present 3 kinds of universal sketches for various things. Probably I will not have time to present all of them, but at least I'll try. And then we'll conclude. So let's start with a question. Anyone knows what kind of creature is this?
A dog.
Box?
Yes, good. It's actually a puppy. Right? Do you know what kind of breed?
Flat.
Well,
all right, so we will come back to this question. Let's all right, let just me remind you of what Piotr already presented, right? Which is a streaming model. I'll be very informal. This is an insertion-only model. So we observe a sequence of elements, right? Each element is from some domain of size n. Frequency of a vector of particular number is the number of times I observe it. It's really a frequency. A frequency vector is just a vector of all those frequencies. Okay, and we have a function from Rn to R that we would like to approximate. But specifically what we want is a multiplicative 1 plus epsilon approximation with some reasonable probability of success that we can amplify. And what makes this problem interesting is that we allow ourselves a single pass over our stream and sublinear space. Sublinear both in the size of our domain and in the size of our data. Okay, very well. And so, as we all know, one of the most powerful tools in this model sketches. And so very informally, what is a sketch? Again, if you have a point in a Rn and a function that you want to approximate, a sketch is some sort of dimensionality reduction tool, right? So we can map our points from a Rn to much smaller space. And we have some parameters, let's say epsilon is the error parameter, delta is a confidence parameter, right? And we have some recovery function that is less interesting that we can run offline. What's interesting is that in the streaming or in other models, we can compute the sketch and then basically work only with the sketch, right? And so the space instead of n, function of n will be function of r, which is much smaller. And this is has many applications, and we will maybe talk about some of these applications. Okay, so this idea of sketches can be extended in many ways, right? And what I want to talk today about is one such way, which is sketches for several functions, right? So if you have many functions, then typically each such function requires a separate sketch, right? A standalone sketch. And usually it is a piece of art, right? It's something very nice, very beautiful, and very complex. And for each new function, we need to compute a new sketch, right? So if we do it naively, if you want to compute approximations for all those functions, we need a space which is the sum of all spaces, right? So sketch 1, sketch 2, sketch 3. So then, of course, there is this natural question, could we do something better? Can we use a single sketch and somehow approximate a family of functions, not just one function, but many functions at the same time? And then other questions such as can we do this in a streaming model, and of course can we do it in small space? What is the actual space complexity for those functions? So this is a very broad.
Universal, fully universal is probably not.
Yes, of course. So universal is somewhat misleading. What we mean universal for a family of functions, and I will talk about this. But for historical reasons, this is how it was called originally, so that's why. You're absolutely correct. So let me be a little bit more precise. Let's say I have a family f of functions, right? And we say that the sketch is universal sketch for that particular family. If we can recover, so we compute, if given a point, we compute a sketch of this point, and then we can recover any function from that family, just from the sketch. Okay.
Yeah, so if you change the multiplicative epsilon to additive epsilon, then it's exactly the question of what is learnable, which we kind of know much about.
Interesting. Yes. Okay. So, this is also one of the first questions in the Sublinear info. This question was asked by Gilani, and it's slightly more different than the question that I presented. But so this is a turnstile model and some other things. But yeah, so. All right, and so that's a subset of what people can do in this. And as Shai said, this is not a new question, really, right? So people ask this question in many forms, in many different domains. For example, Dufferland and Torup and many others consider this similar question for subset sums in the context of databases, right? And the question there was, can you sample? How many samples do you need to approximate various sums, right? And there's a recent paper by Bakim, Lucis, and Latanzi that also considers core sets for various K clustering problems. Okay, and so what I will do today, I will try, if I will have time, to talk a few of these papers, and I will start with this, which is a motivation. Okay, so intuitively it is clear to all of us this is an important theoretical question, but it turns out it also has many practical applications. So I'll try to explain them. Okay, so let me talk about this for the next probably 10 minutes. How many of you have heard about software-defined networks? Okay, so quite a few. Good. So yeah, so this is a recent paper, fairly recent paper with my colleague Vaya Sekar and my former students Alan and Greg, and with Antonis, who former student of Vyas as well. And Vyas was invited to give a talk about this result at Stock 2018, and we got some funding to continue this research. So let me very briefly explain, very informally, what the software-defined networks are. I guess my understanding of networks from my undergrad class of networks was something like this. A network is a graph that is very robust, right? So we have predefined protocols, TCP/IP, UDP, and things like that. Very robust and predefined pieces of hardware, right? And usually static, some sort of static topology. Right? And algorithms that we use are usually optimized for those protocols. And what's important to also observe is that usually it's very difficult to make changes. Right? It's such a robust thing that it is usually very difficult to change anything that you want. Okay. For a reason that this hardware is just a black box, we cannot really look inside and things like that. Okay, so this is a standard understanding of how networks work, right? And until fairly recently, this is how people were thinking about this. But about 10, maybe 15 years ago, people came up with this really simple and transformative idea of software-defined networks. And without going into too many details, the main idea is the following. Right? Imagine that you control a segment of a network. Maybe it's your data center or cloud or something like that. And because you control everything, you can change everything, right? And in fact, you do want to change many things, right? You want to be very flexible because it depends on various problems that you want to address, etc., etc. And so they propose a very simple change, right? Split the network into two abstract, I would say, pieces, right? One is a brain or controller. The controller knows everything about the network. He knows what's where. He can change topology and it can change all protocols and basically all the way that we can communicate. And the body, which is a data plane, which consists from various routers or switches that are usually pieces of hardware or even software that are simple, right, and optimized for speed, usually, right? So they have to be very, very fast. Okay. And this gives you extreme power, right? So for example, what you can do when a packet comes to the edge, right, into your area, right, you can change it to arbitrary protocol, send it in any way you want. You can change the topology on the way, and then you send it back. Okay. And this gives us extreme, gives us a very flexible way to deal with communication, and it allows to speed up and be very dynamic and do many, many other nice things. Okay. So just give you a few examples of why this is impactful. The market for this is projected to be 8 billion by 2021. AT&T claims that by 2020, 75% of traffic will be supported by SDN. And in fact, it is already a non-trivial percentage. So a good chance that when you use your cell phone, it somehow uses SDN in some way. And Google proposed something called Jupyter that handles petabytes of data, and it's also based on SDN. So it's something that is already very impactful and will become even more impactful in the future. Why I'm talking about this? Because it's important to understand, because this is such impactful idea, what are the limitations and what are the requirements, right? And it has many non-trivial limitations, right? So state-of-the-art barefoot Tafina switch, which is one of the leading startups in this area, can send 6.5 terabytes of data per second, right? So it's something very, very fast, right? And it comes with a price, and the price is the following. Very small memory, right? So maybe megabytes of memory, and very small time. It's actually constant time per packet, right? I only can spend a few operations per each packet. So it's really a streaming model. What you're observing here, it's really a streaming model. And on top of this, the language, they really had to simplify the language that they use in a very strict way. P4 is the main language for this kind of this language does not support most data structures. Okay. And but at the same time, as with any other networking environment, we need to answer various questions, right? And especially important questions of network monitoring, right? And those questions, many of us are familiar with those questions, right? These questions of heavy hitters, changes, L0 estimations, etc., right? Out of order packets. Okay, very well. So the standard way to deal with network monitoring is, and this is what has been implemented so far, is using uniform sampling. It's a very naive way, right? It's called NetFlow. This is what Cisco has implemented. And it's a very, very simple way, right? So we just, every packet is sampled with certain probability, and I collect all the samples, send them to the controller, and that's it. And this works very well. In fact, it is a universal sketch in some extent, because we can approximate whatever we want, but the guarantees are not very good, right? I mean, this is also well known that uniform sampling is not what we want. And then there was a lot of work on sketches in this domain, right? Many sketches are known, many sketches have been used. And let me try now to explain. So let's go back and revisit those requirements, right? So as I said, the most difficult requirements here is that the update time has to be constant, right? Because the update time has to be constant, I cannot really install more than a few sketches, right? So if I have to change later on something, right, or if I have to add or delete, it's becoming more and more difficult. And so the idea that we employed was exactly to use a universal sketch, right, and in a very simple way, which is the following, right? When I observe a new packet, I update some counter in the sketch, and periodically I send just one sketch, and then I can extract whatever I want from that particular sketch. Okay? So this hopefully motivates why, at least in this scenario, we do want to compute something that is universal. And then we had some experiments, and indeed you can see that as the number of sketches grow, we can beat just a naive application with the same fixed budget of memory, of course. Okay, so let me now, much time? Let me now very briefly maybe explain universal sketches for various functions. And I'll start with what is known GSUM functions. And I will give very brief intuition for this. Okay, so what is a GSUM function? This is a family of this form, is the sum over all I in my frequency vector of some function of the form g of vi, where g is increasing in this case. Okay. Various other results. So the informal theorem states something like this. If g, and this is not precise, but just for the sake of very short explanation, if g grows slower than quadratic, then we can approximate, and we can approximate any such function using a single universal sketch. Okay. Let me try to explain why. How does it work? And I will explain this just for on a very simple example, which is frequency moments, right? Where p is in the range, excuse me, is in the range from 1 to 2. Okay, so this LP norms for p from 1 to 2. And of course, there has been already a lot of work, right, on this, and this is a very small subset of this work, and many people in this room have contributed. In particular, stable distributions by Piotr can solve this case, right? Frequency moments for p from 1 to 2. So what I want to explain, how can we do it with a single sketch? Okay, so here is a very simple idea. Consider two cases. Case number one, when we have a heavy hitter. Right? What does it mean that we have a heavy hitter? We have a single element in our frequency vector that dominates the rest, right? So one element is larger than the rest. So let's consider this, for example, of frequency for frequency moments. Right? Okay. Here is a very simple claim that says something like that. If I have Fp heavy element, it's also F2 heavy. Why this is the case? Well, because these two norms are related in this way, right? Therefore, with a simple distribution. Okay. But what do we know? We know that F2 heaviness is easy, right? We can find F2 heavy hitters using MS sketch or count sketch on things like that. And so this is exactly the entire idea of this approach, right? So if I have Fp heavy element, I can invoke an algorithm for F2 heavy element, and I am guaranteed that I will find also Fp heavy element. Right? So it doesn't matter which function I'm considering, as long as I have algorithm for F2 heavy hitters, I also can find FP heavy hitters, or more generally G heavy hitters. So that's for the case when I do have a heavy hitter inside. Right? And let's consider the opposite case when I don't have any heavy hitters. Right? Basically, it's no element dominates, no element can contribute more than a small fraction. Right? In this case, we can just invoke some kind of recursive argument, basically sample every element with certain probabilities, probability half, reduce the support of a vector by approximately half, and preserve the value. Right? And so the whole idea of this universal sketches for G-sum is the sketch is just a collection of F2 heavy hitters on various subsampled levels of my stream. Okay. The depth of this recursion is log n, so therefore I only need log n levels of heavy hitters, and such sketch is completely independent of the function. Right? It only depends on F2. Okay, so therefore it is universal. Does it make sense? So that's a very simple and intuitive explanation of what is going on. I'm omitting many details in this case. Okay, now let me show something a little bit more complicated. And this universal sketches for symmetric norms. I think Robbie already presented this result at the beginning, right? Maybe a few months ago. But perhaps it still will be interesting for some of it. And I will talk about universality mostly. Okay, so this is based on a work with Jaroslav Blaziok, Steve Chestnut, Robbie, and Lin Yang. So what is the symmetric norm? Norm is symmetric if it is a norm. It is invariant under coordinate permutation. So it doesn't matter how I permute my entries, the norm stays the same. And it is invariant under sign flips. So basically it's defined by absolute values. The various examples of symmetric norms. First of all, the LP is symmetric. Right? Top K norm, I just sum up absolute values of top K elements is symmetric. A generalization of LP, which is known as Orlich norms, are also symmetric, and etc., etc. And this is a nice norm that is used in machine learning, and it's also symmetric, so we can support it as well. Okay. Not every norm is symmetric, as most matrix norms are not symmetric. For example, Schatten P norm is not symmetric as long if P is not equal to 2. And it's easy to see here. If you take a matrix and permute it, you can completely destroy, completely change the norm. Okay, so let me try to explain the result itself, and then I will very briefly explain the algorithm. So consider a sphere in a Rn equipped with a Haar measure, and consider a function that is continuous on the sphere. We can define two quantities. One is a supremum of the sphere, and another in the median in terms of the Haar measure. The ratio between these two numbers is basically what governs the space complexity of symmetric norms, right? So you can think of it as a ratio between the largest value and the expected value to some extent, right? Almost governs, so the exact statement is that we need to consider this ratio, but not only on Rn, but on all Rn primes for n primes smaller than n as well. And we can only, it is enough to consider only such prefixes because of the symmetry, because we can basically permute without changing the norm. Okay, so MMC is a maximum over all such ratios, over all n primes smaller than n. Our statement says something for the upper bound. We give one path universal algorithm that approximates any such norm with the property that MMC squared is bounded by something and uses MMC squared space. And the same number is required. Basically, it is optimum up to parallel factors. And what's, I think, yes.
Sorry, so this sketch works for all symmetric norms with MMC less than some value?
Yeah. So more generally, if you have a budget of space, right, you can compute all symmetric norms such that MMC is smaller than this budget. And using one sketch, we can compute simultaneously all norms. So it's not even for each, it is for all. So the same probability gives us approximation of all norms. So here is an example of these numbers and how it coincides with the known results for streaming complexity of LP norms, right? So for L1, a supremum is square root of n, and median is approximately square root of n. So the MC and MMC as well is roughly 1. For L2, of course, everything is 1. And for LP, for P larger than 2, B is 1, and M is approximately n to the 1 over P minus half. Yes.
If you apply it with some bound on the MMC to something that has a higher MMC, are all bets off, or does the error degrade?
That's a very good question. I think we can guarantee some sort of approximation, right?
So I didn't hear the question.
If we don't allow MMC space, but less than MMC space. So we have also a result that says the following. I didn't write it carefully, that if you only want, let's say, D approximation, then you allow yourself something like MMC divided by D space, or MMC divided by D squared, something like this. So you have a trade-off immediately. Okay. And so now if you square this, you see that this is exactly the space complexity of streaming algorithms for LP norms. Okay, now let me very briefly try to explain again, without too many details, how we can compute. So I will concentrate on universality, how we get universal sketch. So the most critical property that we will use is monotonicity of symmetric norms. Monotonicity means that if I increase the value of my vector, then the corresponding norm cannot go down. So it can only increase. Okay, and this follows fairly straightforwardly from the symmetry. Okay, so let me try to explain the main idea. This idea, I think, first appeared in the paper by David and Piotr, and we sort of use it. The idea is the following. If I take my vector, V, and I split it in what we call levels, when each entry, so again, this is an insertion-only model, so I can assume that all coordinates are non-negative. I split them into levels where elements in each level are sandwiched between powers of alpha. And I have Bi, it's a cardinality of each level, so how many elements I have. Okay. And V prime is a modified vector where I sort all my coordinates, I round them and I sort them according to the values of alpha. Okay. And because the stream is, if you remember, the stream is of size m, and every time we update the frequency by at most 1, we have at most something like log m possible levels. Right, so the first observation that we can make is that the norm of this modified and sorted vector is approximately the norm of my original vector. Right? Why is that? It follows from the monotonicity and from symmetry. Right? So if I sort it, I don't change anything, and if I increase the values by a little bit, I also don't change. Okay, and more than that, this is a little bit more difficult to prove. Even if I approximate each BI, so even if I don't get this exactly, but only get it approximately, let's say with 1 plus minus epsilon, then I still get a good approximation of the norm. Okay, very well. So now we will work with this modified vector v prime, and more than that, let's split it into t vectors, right? So, and vector, let's call it a level vector, hi. In hi, in level I delete everything, I zero everything except for elements in level number I. Okay. Now again, for the sake, I will not explain how to get 1 plus epsilon approximation, but it's very easy to understand how we can get, let's say, a log m approximation. All we need to do is to approximate a norm of the heaviest level, right? So let's say one of these levels is heaviest. Without loss of generality, let it be the first level, right? And from properties of the norm, fairly easy follows that we can sandwich it by a constant from one hand and one log n from another side. So the only thing that is left is to approximate this heaviest level somehow. And this part I will not explain, but you can show that if you have such heavy level, then similarly to the case with G sum, it implies that B1 is not only heavy in L in our norm, but it's also heavy in L2 sense. Right? So this level will be also heavy in L2 sense, and therefore, by invoking MS sketches or count sketches or things like that, we can also fairly well approximate B1. Okay, so does that make sense? And again, we observe the same thing here. We go from arbitrary symmetric norm to L2, right? So it becomes independent of our norm, and it only depends on this number, on MRC. Later on, when I want to recover the actual norm, of course, I have to apply a different function. But just to construct a sketch, all I need to do is to find various L2 heavy hitters. And therefore, this algorithm is universal as well. Any questions? All right, so I have 8 minutes, I didn't realize. Let me go to conclusion, and if I will still have time, maybe I'll show something else. So to conclude, we have shown that universal sketches are useful in various applications. We also discussed algorithms for universal sketches for symmetric norms and for other families. And the many interesting open problems, such as universal sketches for more general families of norms, graph problems, etc., etc. So let me go back to this. Let me maybe, how about now? The same dog just woke up. So no? Okay, so this is Shiba Inu. It's a famous Japanese dog. And it's famous, it's very cute and happy dog. And one thing that is known about Shiba Inu is that it's really half dog and half cat. Okay, so if you Google it, you can find 8 ways in which Shiba Inu is more cat than a dog. For example, it can climb on trees and things like that, and like to chase feathers on a string. So in our language, it's a universal pet for a family of dogs. All right, so let me maybe stop here. Thank you so much.
Any questions to Vova?
So I didn't get understand. Is the guarantee for that the same sketch works for all F in a certain family with certain probability?
So it's a very good question. I omitted it sort of, yes. For symmetric norms, we have this for all. So I guess what you're asking is this for each or for all, right? Yeah. So for symmetric norms, we have a for all, which is sort of surprising because we have an infinite family of such numbers.
It's kind of universal, what you call universal convergence.
Right. It's actually very interesting to find. I think we could develop this connection with learning, which is.
What are the limitations? So to what extent, so are there any natural families that you know that you cannot do anything?
That's a good question. I think there is, I don't know, but I think for matrices is very difficult to do something at this point.
Like the divergences.
Get some sort of universality for maybe various matrix norms. I'm not sure.
Because it's my understanding that in general there is no universality.
No, of course not.
So the question is, are there any
What are
natural
those?
families where you can say nothing can be done?
I guess what you're looking for is like a family that individual members can be sketched, but not all of them, right? So.
No, if you want worst case, then it's easy to come up with like something random, but you want something like which is nice, but then doesn't have this problem.
Exactly.
You mean you have to, like each norm, for example, you can recover fairly easy, but the entire thing is not, right?
What you skipped carefully is something.
This is, I think, related to our papers that I didn't have time to explain. Perhaps I can try.
Is this something you want to?
Maybe very quickly. Yeah. So I think this is one of the things that we can talk about. So this is a recent paper with Robbie and with Lin, and here we consider a family that is specified by set systems. I didn't have time to explain this, unfortunately, but I think this might answer your question. And let's say a set system that is just a subset, right? So each one of those is easy because it's L0, right? So we can compute. But the collection as a whole, now we want to. Yes. So we find something like VC dimension.
Something a bit related to the for all question. Are the errors kind of related or arbitrary? Meaning, if I overshoot in L2 norm, do I also overshoot in like L17, or could I like overestimate in L2 but have an estimate that's below the actual value in L1? Like, am I biased the same way over all possible symmetric norms?
Oh, you mean can we relate the errors?
Yeah,
for
at
variance?
least in some qualitative sense like that.
That's a good question. I don't know. I mean, I have to think about this. I don't know. I think yes, but okay.
All right. So thanks again.